So we are told that the angle of incidence is 30 degrees. The absolute index of refraction of crown glass is 1.52. And the speed of light in the glass is, so V, speed of light in the crown glass is 1.97 times 10 exponent 8 meter per second. What is the angle of refraction? So we can use two different methods in doing this. First, we can use Snell's law. We can use Snell's law, which is absolute refractive index is equal to sine of I over sine of R. Once we have I, we have the absolute refractive index, we can easily find the angle of refraction divided by sine R. Therefore, sine R will be equal to sine 30 degrees divided by 1.52. Sine 30 is 0.5 divided by 1.52. And what is 0.5 divided by 1.52? 0.5 divided by 1.52, this is 0.32895. Therefore, R will be the sine inverse of this value, 0.32895. And what is the sine inverse of that? Yes. What is the sine inverse of the decimal value there?
19.21.
19.2 what?
21.
21.
Yes, please.
So it's approximately 19 rather. So this is approximately 19 degrees. Okay. The other second method is that for any two composite or media, the product of the absolute refractive index of the first one and the sine of the angle of incidence is equal to the product of the absolute refractive index of the second one and the sine of the angle of refraction. Now, since what we are given as a refractive index of crown glass is absolute, it means the first medium is air, and the refractive index of air is just 1. So it's like 1 times sine of 30 degrees is equal to the refractive index of crown glass, which is 1.52 times sine R. So it gives us the same expression of sine 30 divided by 1.52. This is still the same as 0.5 over 1.352, which will be equal to exactly as we had. Therefore, R is equal to the sine inverse of 0.32895, and R is equal to 19 degrees. So these are the various ways to go about the problem. Any question? Is there any question? Okay, just give me a minute to drop attendance, okay? A lot of us are not around today. It's so bad. Total internal reflection. Total internal reflection. So yesterday we looked at one key, or I think we discussed the conditions necessary for total internal reflection to occur. And one of it is that light must travel from a more dense medium to a less dense medium. Light must travel from a more dense medium into a less dense medium. And the second condition is that the angle of incidence in the more dense medium must be greater than the critical angle of the material or of the more dense medium. So we looked at whenever light travels from glass to air. So the light is from glass, whose refractive index is mu g, and coming out from air, whose refractive index is mu r. So mu d and mu r. The d for the glass means that refractive index of dense medium. Mu r. R for the air means the refractive index of rare medium. Rare also means less dense medium. So the light, to satisfy the condition, light must come from glass and then emerge through air. So since this is the incident ray and this is the angle of incidence, light is emerging through air. So this is the refracted ray. And because light is from more dense medium to a less dense medium, the deviation of light will occur away from the normal. So this will be equal to the angle of refraction R. Now, whenever light hits at a transparent boundary, part of the incident light is reflected and part is refracted. So let's show a ray of light indicating the weaker reflected ray. So this is the reflected ray obeying the laws of reflection. This is also I. Angle of incidence is equal to angle of reflection. Okay, now all that we want to do is that we want to be varying the angle of incidence progressively. So if we are beginning with a lesser value of I, we are increasing the angle of incidence in the more dense medium gradually. So as can be seen, this angle is less than this angle. Okay. Now we realize that this is, I said, this is weaker. This is stronger or brighter in intensity. So as you increase the angle of incidence in the more dense medium, you realize that the light will be refracted away from the normal, the more. So the angle of refraction is also increasing. What we are doing is that we are increasing it gradually. Maybe from 30, if we are starting from 30, 35, 40, 45, so we are increasing it gradually. And as we do so, we realize that the angle of refraction also widens, or the refracted ray deviates away from the normal, the more. Now, as we increase the angle of incidence in the denser medium, a particular angle of incidence would cause the angle of refraction to be equal to 90 degrees exactly. So a particular angle of incidence in the more dense medium would cause the angle of refraction to be exactly 90 degrees. Now, class, if the angle of refraction is 90, the refracted ray this time around will lie on the boundary between the two media. So that is why I'm using the pink to indicate the refracted ray lying on the boundary as we get to that angle. And when this occurs, the whole angle of refraction this time is equal to 90 degrees. Oh, okay. Let me undo and come back. Good. $90. Now this angle of incidence, meaning this whole angle, we are assuming that's that angle in the denser medium, which gave us an angle of refraction of 90. This angle of incidence in the denser medium is known as the critical angle. This angle of incidence in the denser medium that produce an angle of refraction of 90 degrees in the less dense medium is known as the critical angle. So class, the question is, what is critical angle? Can somebody help by the explanation given? Can somebody help us understand what critical angle means? Anybody? Anita, are you here? Okay, Gideon.
The angle of incidence that will make the angle.
Gideon, your line is not good. Okay. Okay. A helicum.
That is critical angle is the angle at which an incidence ray hits the surface of an object to make the refracted ray, the angle of refraction 90 degrees.
Okay, more views. A female to help us. Angie.
Sir, please, the critical angle is the angle of incidence in the dense medium that makes the angle of refraction in the less dense medium 90.
Be 90. Thank you. That's awesome. Okay. So we are just assuming that this is the angle in a more dense medium, which is the critical angle. The first medium is glass. The second medium can be air, any less dense medium. So it shouldn't always be air, but it can be any other less dense medium. So we have the incident ray and then getting an angle of refraction of 90 degrees. And when that angle of incidence in the more dense medium is reached, we have the angle of refraction exactly equal to 90 degrees. This angle of incidence in the more dense medium that produces an angle of refraction of 90 is known as the critical angle. So at the critical angle, the refracted ray is just along the boundary. Okay. Now note that still the laws of reflection is obeyed. So at the critical angle, the angle of incidence is equal to the angle of reflection. So if this is C, this is also C. Now, this is the refracted ray, which is still stronger or brighter in intensity. And this is still the reflected ray, which is weaker in intensity. Okay. Now, at the attainment of the critical angle, any further increment in the angle of incidence in the more dense medium would cause what we are calling as total internal reflection. Any further increment in the angle of incidence in the more dense medium would cause total internal reflection. So hold on, let me sketch a diagram to quickly explain this. So this is still the normal. This is the incident ray. This is an angle of incidence I greater than the critical angle. And when this happens, when the angle of incidence is greater than the critical angle, we have total internal reflection occurring. Gideon.
So how can the incidence angle be greater than the angle of the critical angle? Sorry.
I'm coming. So when the angle of incidence is greater than the critical angle, this time we don't have refracted ray, but all that we have is a stronger or brighter reflected ray. Before, the reflected ray was weaker in intensity. But when the angle of incidence in the more dense medium is greater than the critical angle of the material, or is greater than the critical angle, the refracted ray adds up to the reflected ray. And so we do not have refracted, but a complete reflected ray. This is what we call as total internal reflection. So for total internal reflection to occur, the angle of incidence in the more dense medium must be greater than the critical angle. Now Gideon asked the question, how can the angle of incidence be greater than the critical angle? What is critical angle? Critical angle of a material is the angle of incidence in the more dense medium, which produces an angle of refraction of 90. Okay, angle of incidence in a more dense medium, which produces an angle of refraction of 90 degrees in the more dense, in the less dense medium. Okay, now note that every denser material or dense material has its own critical angle. So as we vary the angle of incidence, we'll get to an angle which will be equal to the critical angle of a material. So if supposing our material in question is glass, glass has its own critical angle of about 42 degrees, meaning that if you have glass and you incident light through it at this angle, when the angle of incidence is equal to the critical angle of glass, you have the refracted ray being lying on the boundary, and the angle of refraction is equal to 90. So when you incident an angle and it is equal to the critical angle of that dense material, you cause total internal reflection. And please, that is the reason why we vary the angle of incidence to a particular angle of incidence, which will be equal to the critical angle of that particular material. Please, are you okay? Gideon, are you okay?
So you mean there can be two rays, one having
Okay.
one having the critical angle.
Good. So Angie, ask your question. Quick one.
So please, my network was unstable, so I didn't really understand what was happening. And also, I felt like your words were contradicting when you said, first you said if the angle of incidence is greater than the critical angle, that's when it is total internal refraction. But then you said again that if it is equal to the angle of the critical angle, then it is total internal refraction.
You understand what I meant. You see, note that for critical angle, for total internal reflection to occur, one, light must travel from more dense medium to a less dense medium. Now, these two media, the more dense medium has its own angle of, it has its own critical angle. So if I'm to use you, Angela, as an example, Angela, if light is incidented through you and it is emerging from glass to air, who is a denser medium here? Angela, who is a denser medium here? Is it you or air?
Me.
Good. You have your own critical angle. Different denser media or medium have their own critical angle. And what is the critical angle? That angle which will ensure that the angle of refraction is 90. So if I know your critical angle, then I can cause light to undergo total internal reflection through you. Class, are you okay? Are you okay? Hello, I'm listening.
Somehow.
Yes.
So the idea is that if it is, blessing, I'm coming in, if it is glass air boundary, it means that if I want total internal reflection to occur in glass, I must first know the critical angle of glass, 42. That is why in explaining, we need to vary the angle of incidence till that particular angle we call critical angle, which will ensure that the light, the refracted ray just lies on the boundary, or the angle of refraction gives us an angle of 90. And so if I want to cause total internal reflection to occur in glass, all that I need to know is that I must know the critical angle of glass. If it is 42, then it means to cause total internal reflection, I must incident light to be greater than 42, and I'll have total internal reflection occurring. Angie, are you okay?
Sir, please, does that mean?
So
Sir, please, does that mean
this,
that it's?
Hold on. Angie, go ahead.
Sir, please, does that mean that if the angle of incidence is not is greater than, even if it is greater than the critical angle, it will still cause total internal.
Exactly. All that we require is that the angle of incidence in the more dense medium must be greater than the critical angle of that material for total internal reflection to occur. Blessing, ask your question.
Say, please, I don't get it. So what you're saying is that if the critical angle is greater than the angle of incidence in the glass medium,
No, Blessing, is the other way around. The angle of incidence in the glass must be greater than the critical angle of the glass. Are you okay?
No.
So we must first know the critical angle of Blessing. If I know your critical angle, let's assume your critical angle is 50. Then it implies that to cause total internal reflection of light in you, I must incident the light at an angle greater than 50 degrees. And the 50 degrees is your critical angle. Is that okay?
No.
What's okay, will you hold on? I will explain again. So Gideon,
so I was saying my problem is okay now.
Okay, so let me, for a better understanding, let's go through the same thing again to help those of us who are not so clear. So the first condition for total internal reflection to occur is that light must travel from more dense medium to a less dense medium. Must travel from more dense medium to a less dense medium. So let's have two different media. One is denser, the other one is rare or less dense. So let's assume that the more dense medium is glass, and then the less dense medium is air. So let's draw a normal. Here's a normal. Now we are incidenting light within the dense medium because the first condition is that light must travel from more dense medium into a less dense medium. So this is the incident ray. So we are first calling this as I, meaning we are assuming we don't know the critical angle of glass. So if one thing that we know is that because light is from glass to air, the refracted ray will bend away from the normal. So we have something like this. So this is the refracted ray, meaning this is the angle of refraction. Blessing, I hope you are following.
Yes, please.
Good. Now, the next thing I want us to do is that we want to increase the angle of incidence gradually in the denser medium gradually. So we are increasing it. This time around, so it means this is I. As we increase it, the angle of refraction will also be increasing. The refracted ray is brighter or stronger in intensity, whereas the reflected ray is weaker. Now, we are progressively increasing the angle of incidence. We have gotten to a certain angle of incidence, which is giving us an angle of refraction of 90 degrees. So at this angle, the refracted ray is exactly on the boundary between the two media. So this is the refracted ray now. So this is the refracted ray. And so we are saying that this angle of incidence in the more dense medium, which gives us an angle of refraction of 90 degrees in the less dense medium, is known as the critical angle. Now, this angle, which we are calling as the critical angle, is that angle of incidence in glass, which will give us an angle of refraction of 90. So it means the moment you vary the angle of incidence and the refracted ray just lies on the boundary, it means you have determined the critical angle of the denser material. Blessing, are you okay?
Yes.
So meaning that if I have glass air and I know that the critical angle of glass is 42, then for total, okay, so let me speak for this. Now, after attaining the critical angle, any further increase, if I increase the angle of incidence a little at any margin, what will happen is that, so I'm increasing the angle of incidence. So this time around, it means that the angle of incidence is greater than the critical angle of the material. Then this is what will happen. Every incident light will be reflected. Every incident light this time will be reflected. And this is what we are calling as total internal reflection. So for total internal reflection to occur, light, the angle of incidence must be greater than the critical angle of that denser material. Angie, have I explained myself?
Yes, please.
So if I have Anita and I want total internal reflection to occur in Anita, then I must know the critical angle of Anita. Okay, once I have this information, then I can easily cause total internal reflection in Anita. That is all that I'm saying. So for total internal reflection to occur, one, light must be incidented from a more dense medium into a less dense medium. And two, the angle of incidence in the more dense medium must be greater than the critical angle of the material. If you have any question up to this point, please ask. So we went through stages of diagram. Let's go back to God. So the first stage, we were increasing, light was incidented from more dense to less dense, and we're increasing the angle of incidence progressively. And then go to where the angle of refraction is exactly 90 degrees, and that's the critical angle. Now, at the critical angle, any further increase in the angle of incidence, oh, please mute yourself if you haven't done so. Oh, let me. Okay, it's been done. So, when the angle of incidence in the more dense medium is greater than the critical angle, we have total internal reflection. And when it occurs, there wouldn't be a refracted ray, but the refracted ray would add up to the reflected. And this time, the reflected ray, which before was weaker, would be brighter or stronger in intensity. This is total internal reflection. So what is total internal reflection? Total internal reflection, please, I'm giving you just explanation, which afterwards we'll put words together, is the phenomenon whereby when light travels from a more dense medium into a less dense medium, and the angle of incidence in the more dense medium is greater than the critical angle of the material, okay, the incident light is completely reflected. So let's come in. Alikam.
Yeah, please, if you are given a question, and then would they in the question will you be given the critical angle of the more dense medium
Can you take your
always?
time? I want to write
Oh, don't worry. I will solve questions, so don't worry. Okay. The total internal reflection is the phenomenon whereby light traveling from a more dense medium into a less dense is completely or totally reflected when the angle of incidence is greater than the critical angle of the denser medium. Okay, so it's a phenomenon whereby light traveling from a more dense medium into a less dense medium is completely or totally reflected when the angle of incidence is greater than the critical angle of the denser medium. That's all. Okay, please note that different materials have different critical angle or angles. Therefore, knowing the critical angle of a material is the requirement for TIR. TIR, I mean total internal reflection for short. TIR to occur. So if you want to cause TIR in a material, just look out for the critical angle of the material and you are good to go. That's all that I'm saying. Okay. Is there any question? I want to drop a second attendance. Isabella. Mm-hmm.
Please, can you explain the notes again? I didn't really get it.
Okay, so all that I'm saying is that if you want total internal reflection to occur in a material, you must first know the critical angle of that material. Okay, Isabella, what is critical angle? It is the critical angle is defined as the angle of incidence in a more dense medium, which will cause an angle of refraction of 90 in a less dense medium. So if you have an idea of the critical angle of the material, you can easily cause total internal reflection to occur in that particular material. Isabella, are you fine?
Yes, sir.
So let's look at how do we calculate the critical angle of a material? Because we are just learning that, to cause total internal reflection, okay, we must first know the critical angle of a material. So how do I calculate the critical angle in order to cause total internal reflection in a particular material? So let's have, there's a boundary separating a more dense medium. Please, it can be any other more dense medium. I'm always using glass, but know that it can be any more dense medium, any other more dense medium and less dense medium. Gideon. Gideon, your line is breaking. Your line is breaking. I can hardly hear you. Your line is breaking.
Can you go back? I want to take a screenshot.
I'm coming.
Sir, please, can you hear me now?
Yeah, I'm coming. Hold on, I'm coming. You give your hurry up. Is it this page?
Yes, sir. Please, thank you.
Hurry up.
Sir, please, I'm done. Sir, please, thank you.
Okay. All right. So we are just assuming that we are at the critical angle of the material. So C. So if we are at the, we have an idea of the critical angle of the material, then the refracted ray is just here. It's just on the boundary. So we have this as 90 degrees. Let's assume the refractive index of glass is mu D. And the refractive index of air is mu R. The D suggests denser medium. R suggests rare medium or less dense medium. You can also choose to represent that by mu R. Now, for any two composite media, the product of the refractive index of the first medium and the sine of the angle of incidence. Our angle of incidence is the critical angle, so sine C must be equal to the product of the refractive index of the second medium and the sine of the angle of refraction in the second medium. Now, the angle of incidence in the more dense medium is the critical angle because, as I told you, that's a requirement. And when this requirement is attained, the angle of refraction is 90. So that is why we have here sine C and sine 90. Class, are you okay? Are you okay here? Are we fine? Why Sine C and sine. The requirement is that if you know the critical angle of the material, you can easily determine total internal or cause total internal reflection. So we are saying that if the angle of incidence is equal to the critical angle of the material, then the angle of refraction is 90. So the whole thing is similar to the product of the refractive index sine of the angle of incidence is equal to the product of the refractive index of the second one times the sine of the angle of refraction, R. But our angle of incidence is a critical angle, so I is equal to C, and R is, when I is equal to C, R is also equal to 90. So that is why you see sine C and sine 90 here. Are you okay? Frank?
So this is only when I is greater than C.
No, we are not there yet. We are not at I is equal to C. The requirement is that to cause total internal reflection, you must first know the critical angle of the material. So I am assuming that let the critical angle of the material be C. And when you are at the critical angle of the refraction, Frank, of the material, Frank, what would be the angle of refraction?
Please come again.
When the angle of incidence is equal to the critical angle, what will be the angle of refraction?
Is there 90 degrees?
Exactly. So I just want to know, we are just looking for an expression which will help us calculate the critical angle of the material. That's why we are pegging I at C and not greater. Are you okay?
Yes, sir.
So mu D times sine C is equal to mu R times sine 90 is 1. Therefore, sine C is equal to mu R divided by mu D. Therefore, C will be equal to the sine inverse of this ratio, the refractive index of the less dense medium divided by the refractive index of the more dense medium. Okay. Now, look at something. If the less dense or the rare medium, if the rare medium is air, if the less dense medium is air, because the refractive index of air and vacuum is equal to 1, this expression for the critical angle sine C would be equal to 1 over the absolute refractive index of the denser medium, which in most situations or in most books written as 1 over n. Don't forget n is another symbol for refractive index. So if the less dense medium is air, then sine C is equal to 1 over the absolute refractive index of the denser medium. And in this case, the critical angle will simply be equal to the sine inverse of 1 over n. If the refractive, if the less dense medium is not air, note that this is what will happen. Then sine C will be equal to the refractive index of the less dense medium divided by the refractive index of the denser medium. That is the difference. So this is an expression to help us 1 and 2 are expressions to help us calculate the critical angle of the more dense medium. 1, if the less dense medium is air, and 2, if the less dense medium is not air, but any other material. Please ask question if you have one. Ask questions if you have one. Frank.
So the refractive index of air is sine 90. That's 1.
No. No. The refractive index of air is equal to 1. Air and vacuum is equal to 1. That is how come I represented this by 1. Oh, I get your question. No, Frank, sine 90 is 1. Sine 90 is 1. Okay. But if the refractive index, the less dense medium is air, then the refractive index of the rare medium will also be 1. So it's like more or less like 1 times 1.
Yes,
Frank,
sir.
are you okay?
Yes, please.
That's all. Anita, any question?
No, sir.
Okay. Yasmin.
Sir, so
Yes.
does it mean that the critical angle be equals to the angle of reflection?
Oh yes, yes. It also obeys the law. So under this consideration, when the angle of incidence is equal to the critical angle of the material, the angle of reflection is equal to the critical angle.
Okay.
Gideon.
So please, can you differ mu D and the mu R?
Pardon?
So
Gideon, I'm
the
listening.
mu D and the mu R.
R is the rare medium.
So
Rare, it's okay. Rare medium also means less dense medium. So the R simply means rare, which is less dense medium. Okay. And the mu D is the refractive index of the denser medium or of the dense medium. Are you okay?
Yes, sir, please, thank you.
All right. I'm looking for a question so we can try. Okay, so calculate the critical angle of crown glass. Calculate the critical angle of crown glass if the angle if the critical the refractive index of crown glass is 1.52. Calculate the critical angle of crown glass if the absolute refractive index of crown glass is 1.52. if the absolute refractive index of crown glass is 1.52. Yes, Frank.
Sir, please can you repeat the question again? I didn't hear it well.
Calculate the critical angle of crown glass if the absolute refractive index of the crown glass is 1.52. Elikem.
So please, I had 41.14, please.
Okay. We'll discuss it afterwards. Oh, don't worry. I'm writing. Want to give you another question. So we have this diagram. You are given the absolute refractive index of the first medium, which is air, to be 1. The absolute refractive index of the second medium, which is the plate X, is 1.4. Then the absolute refractive index of the plate Y is 1.7. And since the other medium is the absolute refractive index of air 1.0 or 1. Now the first question says that what is the sign of the critical angle for the light ray at the boundary between plate Y and the air? At the boundary between plate Y and the air. Okay, what is the sign of the critical angle for the light ray at the boundary between the plate Y and the air? And then the next question is that determine the critical angle of plate Y. So B, determine the critical angle of plate Y and the C question is that calculate the angle of incidence theta. The angle of incidence theta. So the first question, we know that once the absolute refractive index of crown glass is 1.52, then sine C is equal to 1 over the absolute refractive index of crown glass. Therefore, this will be equal to 1 divided by 1.52. Okay, therefore C would be equal to the sine inverse of 1 over 1.52. Let me check to confirm the exact value. So please attempt the second question. Let's see what you can. Please, when you are doing this, just be sure that your calculator angular measurement is in degree. If it is in radian, it will affect your value. So whatever you'll be writing will be wrong. Okay. So just make sure that your calculator's angular measurement is in degree. So this is the critical angle is approximately 41.1 degree, or 41, approximately 41 degrees. So what is the sign of the critical angle for the light ray at a boundary between plate Y and the air? This is the boundary between plate Y and the air. Okay. Has somebody managed to finish?
Sir, please. I had sign C is equal to 0.59.
0.59. We shall see. Who else had a same or different value? If you got the same or a different value, I think this is correct.
So please, I got this.
Oh, okay, I think that is right. Then B, determine the critical angle of plate Y.
So I had 36.16 degrees.
Okay, so 0.59. And then what's your answer again?
36.16.
So approximately 36.2 degrees. We shall confirm. And then the last question, calculate the angle of incidence theta. The angle of incidence theta. Hey, let's hurry up. We have about 8 minutes to go. Okay, so let's discuss it. Let's discuss it. We have to calculate the sign of the critical angle between the light ray for the light ray at a boundary between plate Y and X. So if the talk is about critical angle, then it means that the angle of refraction in the air must be 90. If the statement is about the critical angle, then this angle here must be C. This is C, and the angle of refraction must just be on the boundary between the two media. So the refracted ray must just lie on the boundary between plate Y and air. Okay. Then in that case, we can say that this angle is 90. Therefore, the product of the refractive index 1.7 times sine C must be equal to the refractive index of A, which is 1, times sine of 90 degrees. So sine C will be, sine 90 is 1, so 1 over 1.7. And 1 divided by 1.7 is equal to what?
0.59.
0.59. So that's it. Then determine the critical angle of plate Y. So once we have sine C equal to 0.59, C would just be equal to the sine inverse of 0.59. And what's the sine inverse 0.59? This is 36.2. Good. So 36.2, exactly 36 degrees. Yes, Frank.
Sir, please, when I entered it into my calculator, I got 36.03.
For it depends. It depends on how you took. You see, 1 divided by 1.7. 1.7 is a lengthy value, but we approximated it to 2 dp. That is why we had 36.2, and perhaps you use the whole value. Okay.
Yes, sir.
So just usually express we can even, for angles, we can express our values to the nearest degree, 36 degrees. Gideon, you were also trying to ask something.
I think we're also trying to say the same thing, that the angle, you get 36.03.
Oh, that's the US. We are just the whole value is okay. So calculate the angle of incidence. What did you make for the angle of incidence theta?
So this I got 20.01.
20.31. How did you get it?
So this, because the new angle of incidence on the plate Y was the critical angle. So I just put it into the Snell's law, but then I used the refractive index of the plate Y. That was 1.7.
So that's correct. You see, in plate, I'm coming in. Within plate Y, the angle of refraction is the critical angle, C. So that would help us find the angle of incidence, okay, in plate X. So let's do it, okay, gradually. Since we have the angle of refraction in plate Y, which is C, we will need this angle. Let's represent this by I. I we know. So if you take the relative refractive index as light moves from plate X to Y, this is also equal to sine of I over sine C. C we know. Now what is relative refractive index? This is the refractive index of Y over the refractive index of X. which is equal to sine C, sine I over sine C. The absolute refractive index of Y is 1.7. Absolute refractive index of X is 1.4. And so we have sine I divided by sine of 36. Okay, so by this, it would give us the angle of incidence in plate X. And that angle of incidence is also the same as this angle of refraction here. So please help me find I. So we have sine I is equal to this ratio, 1.7 over 1.4 times sine 36. Quickly calculate this for me. Please, let's hurry up. Are we through?
So please, it will give you 0.7137, like so 0.72.
So what is
No.
I? What is I?
Sir, please.
45.53. 54.
So 35.
45.54.
Is
45.
it? Okay, 45. Please, are you getting the same thing? Let's confirm. Let's confirm. Anita and Co. Elitia, Janelle. Augustine, are you there?
Yes, please.
Let's confirm. So it's I-45.
Yes, sir.
Angie.
So please, I have a question.
Uh-huh.
So please, isn't the incident ray also the same as the emergent ray? So I'm asking if they asked us to find the
No.
angle of incidence, and the angle of incidence would be the same as the emergent ray. So won't the angle of incidence in Y be the critical angle of Y be the angle of incidence?
So here, let's calculate theta. We found I, and I will be equal to the angle here. Okay, I will be equal to the angle here. So use this to find theta for me before I answer you. Elikem.
Sir, for I had 45.56.
Okay, so 45. So we are looking at theta. Let's look at theta. So if I is 45 points, what will be theta? Yes, so theta must be close to theta must be close to almost 90.
So please, it's 81.87.
I'm coming. So sine inverse of 0.9899. 81. Okay, so I got yes, 81 points, approximately 82. Approximately 82. Approximately 82. So this is, it is Angie, your question. We are not getting the same angle of incidence as the angle of emergence because this is a critical angle condition. Okay. And besides,
Okay, sir.
besides, you see, the order is that the refractive index of air must be less than, oh, okay, it follows. It follows. Must be less than the refractive index of plate X and less than the refractive index of plate Y. So it follows. But because of the critical angle condition where the light is incidenting at that special angle, that is right. So please, this is how you have to gradually apply the concept of critical angle in solving problems. Okay, I'll send you a couple of examples, about 2, to try over the weekend so that we can master the application of it. But realize that you have to apply either composite media, I did that, composite media or relative refractive index, and also to apply this formula of critical angle in solving the problem. All right, it says it's even gone 5 minutes past 5. So this is where we end today's show. Okay, your assignment, weekend assignment will follow. But Angie.
Sir, please, I just received news that we're supposed to learn, my school, we're supposed to learn laws of motion and then vectors before we come back to school. I was wondering if you have videos on that I could watch.
Yes. So send me a message, okay? I'll send you videos on those 2 jobs. But remind me.
Okay, sir.
Thank you. Okay. All right. So if you don't have any question, then bye-bye to all of you.